to the last one but one class or lecture of this school. So today this lecture will be by Professor Victor Roy. Victor Roy did his PhD in VCC Kolkata, and now he is a faculty in the physics department at NISER Bhubaneswar, and he will teach you about the hydrodynamics, general hydrodynamics, and also the relativistic hydrodynamics. And one small thing I just wanted to mention about him. Yesterday we were listening a lot of discussion on this hydrodynamics in small systems. So and then there were also several discussions on how you consider the initial state, whether it is you also discussed about the three sports and other things like that. Victor is one of the person who used hydro for small systems long back in 2009, and where we also looked at some aspects of this kind of thing, how you consider proton in the beginning to start with. Depending on that, there is possibility of seeing V2 elliptic flow after hydrodynamic evolution. So Victor, I think you take over now.
Yeah, thank you, Siddhartha, for this nice introduction. I just want to point out here that Siddhartha was the first author in that study, and it was a really great time. I mean, I enjoyed a lot working with him, and I would like to thank the organizer for inviting me to give this lecture. As I can see, some students, I already know them, like there are few students, and they are quite advanced in their PhD study. So I think most of the things that I'm going to discuss here may be familiar to most of you, but I prepared it in such a way so that a first year student can also follow what's going on when we talk about hydrodynamics, specifically hydrodynamics in heavy ion collision. So one more thing that I would like to tell you before I start, please stop me if you have any question. I will try to give answer during the talk itself, and also at the end you can ask. So let me start now. I'm going to presentation mode, and unfortunately my pointer is not working. So please bear with me for that. So as you see, the topic is hydrodynamics in heavy ion collision. Okay. So I prepared the slides in the following way, such that today I will be mostly talking about theoretical aspects, because those things, the ideas, the definitions, those are important in order to understand what's going on in heavy ion collisions, particularly when we talk about hydrodynamic code and the result we obtain from it. So that's why today's talk mostly will be focused on theoretical aspect, and in theory also I mainly focused on the non-relativistic and textbook kind of thing, because I think that if you understand that, then the relativistic extension I will again discuss a little bit about that. It's straightforward, and you will follow most of the argument. Okay, so the outline is like the following. Like first I will discuss the non-relativistic hydrodynamics. I'll start with that, and I will mention what is ideal hydrodynamics and what is viscous hydro. Then I will give a short introduction to relativistic hydrodynamics, and after that, this is the numerical part mostly, that when we'll discuss hydrodynamics in heavy ion collision, and it contains the details, some details about numerical hydrodynamics, which means I will probably use a code, publicly available code, to show you what's going on actually inside or under the hood. And then I will also give you some idea how we connect the hydro, the simulation result to experimental observables. And as I mentioned, some details will be there. Probably these things I will be covering in the next day. Okay. So as I mentioned, our first part will be dedicated discussing the preliminary concept of the textbook ideas. So let us take this example. Like here is a standard textbook on fluid mechanics by Landau, and I will be mostly using this book for the first part. So if you open this book and go to chapter 1, and in the first page, you will see the definition of fluid dynamics is given, and also very few essential ideas are given here as well. So you probably can't see it here on the screen because it's so small. So I will zoom it out. So let's take this initial part, the introduction. Here almost all the ideas related to ideal hydrodynamics, this is the non-relativistic part again, is given. So what are those concepts? So I'll go one by one. The first concept that it deals with, I need to minimize this thing, covers my screen. Excuse me. Okay, I have to leave the full screen mode. Okay. Yeah. So the first point here to note is that the definition of fluid dynamics, as it is clear from the name itself, fluid dynamics concerns with the study of motion of the fluid, which consists of liquid and gas. Now, the second important point to take from this beginning part is the idea of Knudsen number. So what he talks about here, like he's telling us that any small volume of fluid, it actually contains a large number of molecules. So essentially, this is where the fluid dynamic approach works. And in general, when we talk about Knudsen number, it's almost the same thing. So the interparticle distance is much less than the typical system size, or which deals with the fluid volume. Okay. And the third point, where he talks about the fluid element. Sometimes we call fluid as element or fluid as particle, but it does not mean that that we are talking about the individual molecule. Again, it's a small volume element of fluid which contains many numbers of molecules. Okay, now come to the second part here. Here he gives somewhat mathematical description of a fluid. How do we define a state of a fluid? The fluid is in motion. So to define the state of a fluid in motion, we mainly need two things. One is the dynamical variable, and the other part is thermodynamic variable. Now in dynamical variable, if you consider the ideal fluid, then you need to mention what is velocity field. Now I'm talking about here velocity field, and this is one of the important difference between the discrete system, like we study in Newtonian mechanics, dynamics of a single particle or a rigid body. But here in fluid, we have a continuous system. So here the velocity is a field. And for the particle, velocity is a single vector which is associated with the particle itself. Wherever the particle moves, we imagine that the velocity field also moves with that. Sorry, the velocity vector moves with that. But for fluid, which is a continuous medium, you have to specify velocity in all points at any given time, and also all other times. So essentially, velocity, which is a vector, is a function of space coordinate x, y, z, and also time. So this is a field. And same is true for thermodynamic variable. Usually we take pressure field. So this is again a scalar field, and we also have mass density of a fluid. So if we can specify these things as a function of space and time, the state of the fluid is completely defined for this ideal case. Okay. Now the next thing, the next important idea that we need to take into account here is the idea of co-moving derivative. Now again, this is coming because we are dealing with fields, not particles. So what is a co-moving derivative? So let us take this example. So if you have some kind of like pipe inside which the fluid is flowing, so I cannot use the pointer here, but you can see, if you notice in the figure on the left hand side, we have a point where the velocity of a fluid, say for example at time t, is given. So velocity v, you can clearly see the velocity is changing because your cross section of the pipe is changing. So velocity at different points are different. As well as if your source of the water, so water or fluid, whatever fluid is flowing inside the pipe, if your source changes, I mean the rate at which the fluid is pumped through the pipe, it is changing, then even at a given point, the fluid velocity may change as a function of time only. So that time dependence and space dependence, everything is there. So if you consider a fluid element now at time t at this left hand side position, and at time t plus delta t, it goes to this right hand side position. Okay. Now we are talking about how much is the change in velocity. Okay. So let's figure that out for this case. So the dv is the change in velocity, which we can express like this. So we subtract the initial velocity from the final one. Now we use the fact that this velocity vector is a continuous field which has a well-defined derivative at every point. So we can then Taylor expand the first term as follows. It's unfortunate that I cannot use the pointer here. Again, I have to leave probably, then I don't know. Okay, then the whole thing is done. So let me see if I can use the pointer here. Okay. Yeah. So essential point is that we Taylor expand this. Oh no, it's not working. Spotlight. Yeah. So we Taylor expand this term. Okay. And we have the following terms. And you can see that these two terms cancels out. And what you are left with, the following expression. And if you write it in a compact form, then you have the left hand side. Okay, if you take the time derivative dv dt, then the left hand side is the total time derivative, and the right hand side contains the partial time derivative of the velocity, and then another term which is v dot grad v. Now this is true for any other quantity. I mean, we can define a co-moving derivative which is given here like d dt is equivalent to partial del del t plus v dot grad. Now you can plug in velocity here or mass density here or any other vector field here. If it's a part of fluid, then the total time derivative is given by this, and this is called co-moving derivative. Now let me again go to the full screen mode and okay. Oh, now I think the pointer is working, but I have to go through this thing again. Okay, the next important thing is the equation of motion of a fluid, which is also called Euler equation. Now, what is Euler equation? It is essentially the analog of Newton's law, but for a fluid element. Now, what is Newton's law? It tells you that if you consider a fluid element, which is small volume, so its acceleration will be equal to force applied on the small element. Now, the left hand side, as you can see, this is the mass times acceleration, d dt is the total time derivative, but as we have already seen, the total time derivative can be decomposed into two parts, and that should be equal to force. Okay. Now, what is mass? So mass of a fluid element, actually you can write it in terms of density times volume. Okay, that we will use here because we usually talk about density of a fluid. So if you substitute this mass expression in this equation, then you will arrive at the following expression. Note here that we have taken out V common from this left hand side and we have divided the right hand side by the volume V. And the right hand side, it contains now force per unit volume, which is also called a force density. Okay, now what is force density? Let us analyze a little bit using dimension analysis. Okay, so force per unit volume, which is this right hand side term, you can alternatively write like force divided by area times length, because area times length give you volume. Okay, and what is force by area? That is pressure. So essentially you are having pressure by length, and pressure by length means pressure gradient. Okay, the length can be in any direction, so that's why it's the pressure gradient. And why this minus sign? Because if we consider, say for example, this is your fluid element, and you have pressure P on this side at position X, and pressure here is P plus del P del X delta X, where delta X is this increment along this X direction. Then the difference between them is given by this quantity del P del X times delta X. So essentially, if you know how fast the pressure is changing along the X direction, and you multiply the distance over which the two surfaces are separated, then you get the total pressure difference. And as you can see, X increases in this direction, but pressure actually, according to this formulation, it will give you a minus sign. So that minus sign is here, minus gradient of P. Okay, but here we didn't consider any external force, but there may be external force like gravity on a fluid. So if you also take into account that, then you have to add that part to the force term. But remember, this force, small f external, it's a force density. Okay, and this is known as the Euler equation of motion for fluid, ideal fluid. Okay, now one important point to note here, we have this term v dot grad v. Okay, and this is coming in the from the co-moving derivative, and you can alternatively write this in using vector identity, like half grad of v square minus v cross curl of v. Now this v square term, it's essentially giving us a non-linear, it's a source of non-linearity in the hydro equation. So hydro equation essentially is a non-linear system of equation, and as you know that non-linear systems are quite difficult to handle, not like linear system where you can apply the principle of superposition and other well-known ideas of differential equation. So non-linear differential equations are notorious to handle. So that's why it's not possible to find analytic solution for most of the problem related to fluid dynamics. Okay, one more thing we need to consider, take into account. So we talked about here the velocity, how it is changing from point to point, and as we see that the pressure gradient acts as a force, driving force for that. Now what about the density? The density of a fluid, can it change? Yes, it can change. If your fluid is, say for example, compressible fluid, your density may vary in response of a force. So if you consider a fluid element inside a fluid, like this is a small fluid element, and the mass of the fluid element is dm, which you can get by multiplying the density with the small volume dv. Now this mass can change as a function of time, or if the fluid element is moving, then as a function of space as well. How? If there is net flow or net outflow of mass from this small volume, then the mass inside can change as well as the density can change. Okay, and I'm not going to derive, or it's a short derivation, you can try it yourself. But if you take into account the variation in density, that is given by this conservation law, mass conservation law. What it tells, so you have at any given point, the density can change as a function of time due to the flow of mass from that small volume. Okay, so here we consider there is no source inside this small volume. So essentially, in words, change in mass inside a small elemental volume is equal to flow of mass through the surface. Okay, so what now? If you have source inside that small volume, then you have to take into account that as well. So you have a source term here in the mass conservation equation, and in words, it says that change in mass or density in a elemental volume is equal to flow of mass through the surface of that small volume plus the contribution coming from the source. Okay, fine. Now that's all about the ideal hydrodynamics in non-relativistic regime. Now, as we know, any fluid, any real fluid, it contains.
Hello, can I ask a question?
Yes, yes.
Yeah, in the last slide you told something source. So what is the source here?
No, source can be like if you are considering a fluid, then the source can be think of like you have a pipe inserted in that small volume. The end of the pipe is there, and the other end of the pipe is attached to some source of the fluid. So you are essentially pumping fluid into that small volume. That is the source. Or you can take out fluid from that volume element that can also be thought of as a fluid, as a source. Okay, so like if you make an analogy with the electrostatic, then essentially it's the presence of charge inside the small volume, which gives rise to electric field. So charge is a source of electric field. You can think like,
That's why I asked, because you can understand in place of a charge, but
yeah, you can make analogy. Yeah, it's analogous because electric field, sorry, electric field is also a field like a fluid velocity field, and it also follows a similar equation. So this is essentially like the conservation equation. It's still valid for those cases as well. Yeah.
Okay, thank you.
Okay, so as we know that any real fluid, it will resist any relative motion. Okay, relative motion means if there is a velocity gradient inside fluid, it will try to resist it, and it will try to make everything isotropic or with same velocity. Okay, and this thing, the viscosity, is actually analogous to friction in solids. So for solid bodies we have friction, but for fluid we have viscosity. And more specifically, this viscosity are actually coming due to some non-equilibrium processes going inside the fluid. Okay, and they are associated with thermodynamic irreversibility. That means we are generating entropy in these processes, and irreversibility results in energy dissipation in the fluid. Some examples are like if you have shear and bulk viscosity and you have velocity gradient. So velocity gradient acts like a non-equilibrium process here, and the irreversibility means you are trying to go to the maximum entropic state, which is the equilibrium state, where you actually lose some kinetic energy of the relative motion to the fluid as a heat, and you reach the local thermal equilibrium, which is maximum entropic state. And same is true for other dissipative quantities like thermal conduction, etc. Okay, so in more simpler words, we will be only focusing here on the shear viscosity, but the other dissipative quantities you can consider similarly. So what is shear viscosity? Probably most of you are familiar with that, but let me go through that definition once again. So when adjacent layers of a fluid are moving past one another, this motion is resisted by a shearing force which tends to reduce their relative velocity. And this resistance of gradient in fluid velocity is related to the shear viscosity. So probably this is one of the popular picture that you come across when we discuss about viscosity. So what is going on essentially here? So we are generating velocity gradient inside fluid. How you can do that? In laboratory experiment, let's say you take two plates, one is there and another is here, and inside that two plates you have some fluid. Now you are moving the upper plate with some constant velocity. After a certain time, you will notice that the velocity of the fluid will take the following configuration as shown by the arrow here. Now, if you consider a plane, an imaginary plane inside the fluid, then there will be a force, net force on this surface due to the velocity gradient along this direction. Or in other words, so if we take the y-axis along the direction of this thing, and x is the direction of the motion, then you can write force per unit area on this imaginary surface is proportional to actually velocity gradient, how fast the velocity is changing across this surface. And that proportionality constant is known as the shear viscosity coefficient. Okay. Now, as you can see, if eta is large for a given velocity gradient, the force per unit area will be large. And if eta is small, the force per unit area will be small. Now, this eta is also known as dynamic viscosity. Do any one of you know about another viscosity, which is called kinematic viscosity? Are you familiar with the concept of kinematic viscosity? Anyone? Okay, if not, then I suggest you please try to figure it out. What is that? There is another viscosity called kinematic viscosity. In this case, in non-relativistic case, it is defined by dividing eta with the density of the fluid. Eta over rho is called kinematic viscosity. And this quantity is actually I probably, okay, I will have the expression, then I will discuss this in details. One more thing to notice here, that this transport coefficient, this zeta, or if you have bulk viscosity, there is zeta, they are usually a function of temperature. Okay, now, yeah, so now we know that if there is viscosity, then there is a force per unit area inside fluid. But how does the dissipative terms contribute to the fluid equation of motion? Because we have derived the equation of motion for fluid, but that was for ideal case. Now let me write it once again. This was our equation of motion. So remember, you can actually now derive the expression for the dissipative terms from rigorous argument as is given in Landau, but I think it's not a good idea to show all these derivation here. So what I will do here, I will use the dimensional analysis and I will convince you what will be the form of this source, the force due to viscosity in the equation of motion. Okay, now we notice that again the right hand side is force per unit volume. Okay, and as we just have seen that the viscous force per unit area is given by the following expression, eta times del v del y. For our case, it was del vx del y. Okay, but this the dimension of these two things are not matching. One is force per unit volume, another is force per unit area. So what we need to do to match the dimension, we can do one thing. We just consider force per unit volume for this case as well. So that you can achieve by dividing another length scale here. So that will give you eta times a double derivative. So then you have here in below you have one more additional length scale. Okay, and if this is the case, then you guess that this term will you can now add to the force density term, because this additional term is coming due to the viscous force. Now that's almost correct, not exactly. Why this is so? Again, the detailed argument I am not giving here. But if you consider that a fluid, say for example in a cylinder, it is in equilibrium state, and the cylinder is rotating along with the fluid. So there is no relative motion between any adjacent layer of the fluid. The fluid and cylinder rotating with same angular velocity. In that case, since there is no relative velocity, there should not be no viscous force between the adjacent layers. And if you take into account that and the other fact that you want to make the viscous stress to be stressless, then you have the following term, following expression in the equation of motion. So you have now two additional terms, like this term was already there, and you add this just to make sure that in a rotating fluid there is no relative motion and you don't have any viscous force, and this one to make the thing stressless. Okay, this is how it looks like, and this is known as sorry, I didn't write it. This is the Navier-Stokes equation. So here we only consider shear viscosity, but if you consider bulk viscosity, there will be other terms. Now when we will go to the relativistic case, you will see the expressions are quite similar, only there are some correction due to relativistic effects. So that's why I am discussing this thing in details, and I will quickly go through the relativistic part, just giving some analogy with the non-relativistic part. Okay, so far we have derived all these equations, etc., etc. Now I will finish this non-relativistic part, giving you a simple application of hydro equation. So how do we apply this thing, all this equation of motion? I will consider here one of the most simplest possible situation, where essentially we are considering a fluid in a uniform gravitational field and which is at rest. Rest means your velocity fields are zero. So that makes our life much more easy. So the situation is something like this. So on the Earth's surface, we have a container which contains fluid, and the fluid is at rest. But the fluid, it extends up to some height, which we will come to that later. Now we also consider here if the fluid is non-viscous, although it doesn't matter because the velocity is zero anyway. Now what about Euler equation? Euler equation is as follows. So we have this usual term here, F external is the external force due to gravity. So this takes the following form, rho times the gravitational acceleration. So this is the force per unit volume, fluid volume. Now if you take into account the fact that velocity is zero, then this left hand side all terms are zero. What you are left with is the following expression. And if you rearrange this gives you gradient of pressure in the fluid is equal to the external force density. Now, for our case, since we are talking about the variation of gravitational force along the z direction, we can disregard the variation along xy because xy is a symmetry plane here. So we can write the gradient of P as del P del Z, and that is equal to minus rho times G. Again, minus sign is there, which shows you that the gravitational acceleration point downward, whereas our Z increases upward. Okay, if we find this, then we can integrate out easily, and we find the expression for pressure. Now, pressure is, you see, minus rho G times the Z coordinate, and then plus some the integration constant. What is the integration constant? Now, if you say that at Z equal to H is this height, your pressure is equal to the atmospheric pressure, which is P naught. Then pressure is given by the following expression. Okay, and you can verify this because if you set H is equal to Z, then P will be P0 as required. Okay, so fine, we found pressure here only because velocity you already know, the pressure was the other term which we didn't know. And if you know the pressure, you can find the density from the equation of state, which I haven't talked yet. I will talk in a later slide. What is equation of state and why we need this. Now, remember one thing, this is the most simplest possible case. Now, when the fluid is in motion and we have non-zero viscosity as well, the problem becomes much more harder. And that's why it is not, I mean, it is almost always impossible to find analytic solution for most of the cases. Only few selected cases and under certain assumptions, we can figure out what's going on with these fields, pressure field, velocity fields, etc. Okay. Now, so far we have talked about the general textbook things. Now, what is the connection to heavy ion collision? How much time do I have? Okay, 2:30. I should stop at 2:40. Is it, Siddhartha, or 2:45?
Yeah, it is okay. 2:40, 2:45.
Okay, then I will. Okay.
Victor,
Okay.
in principle, you can go up to, let us say, by 3 we will finish your everything, including the discussion.
Okay. No, I'm going a little bit slow because I have a few more things to discuss. So what's the connection to heavy ion collision? So in heavy ion collision, how hydro works and why it is applicable. So let us go back again to Landau, this guy, and he gave us this idea long ago. I think he gave this paper, which you can find in these collected papers of Lev Landau, edited by D. Terher. And there is a paper number 88, which deals with hydrodynamic theory of multiple formation of particles. If you go to that paper, I am just showing a snippet of that. And there he mentioned why hydro will work here in this. This was not heavy ion for heavy ion collision, but this was for high energy particle collision. So it's essentially the elementary particle collision, either proton, or electron, etc. So I would like to highlight here this point. Let me read it out. So what he's saying here, okay, when two nuclei collide, a compound system is formed and energy is released in a small volume V subject to a Lorentz contraction in the direction of motion, okay? And at the instant of collision, a large number of particles are formed. The mean free path in the resulting system is small compared with its dimension and statistical equilibrium is set up. And the second point is, the second stage of the collision consists in the expansion of the system. Here the hydrodynamic approach must be used and the expansion may be regarded as the motion of an ideal fluid. Okay, so as you can see, he already discussed here the idea. Essentially, you dump a lot of energy inside a small volume. Essentially, you create many particles and their interparticle distance is quite small compared to the system size. And you can apply here the ideal hydrodynamics. That's what he claimed. Okay. And nowadays, when we talk about heavy ion collision, our energies are quite large compared to the case when Landau discussed this paper. Okay, and as you can see, we have varying energy and the particle production we can measure in terms of eta and all these things. And later on, we figured out, I mean, Bjorken and others, they figured out that hydro can be applied to heavy ion collision by looking at those experimental observables. observable as well. Yes, that's what is mentioned here in this slide. So although we call it Bjorken's idea that he gave the connection between the final multiplicity to the initial entropy density produced in heavy ion collision by using his well-known Bjorken flow solution. But it is actually a paper by E.C.G. Sudarshan 10 years before Bjorken's paper, it appeared. And there also he essentially discussed the same idea. And he was able to explain the pions transverse, the transverse momentum distribution of pion, as is shown here. So all these ideas came around 1970s and 80s, approximately 40 years after Landau's first paper on hydro. So that's more or less the connection. Now, that's not all. Let us go into a little bit more detail, and we discuss a few physical aspects of this. So one of the physical observable, I mean the experimental observable, as we know, is flow harmonics in heavy ion collision. And you can explain this flow harmonics quite nicely if you assume that the hydro picture works there. Okay. Probably all of you are familiar with this kind of argument, but let me go through for the sake of completeness. So we have two heavy ions colliding. It's an off-central collision, okay, and the overlap zone is like this, almond shape. And usually we have to choose some axis of symmetry, like here we choose x-axis as the impact parameter direction, and y-axis is the perpendicular direction, okay. And then you observe what you observe. This is the initial state, and you observe in the final state the particle momentum distribution. And from the experimental observation, we know that the particle momentum distribution is not isotropic in momentum space. So, and that's what actually how do I say? That's what gave us the idea that maybe hydrodynamic evolution is again working here to give this kind of picture. Now, I will use the non-relativistic expression just to show that what was the idea. So this is Euler equation, but we have now viscous terms added. So if you disregard this, it was the Euler equation, this part. Now what this tells you, the fluid acceleration in response of pressure gradient. Pressure gradient is the force here. Now what about the pressure gradient in this case? So along x-axis, the pressure gradient is like this, and along y-axis, it's like that. And surely the pressure gradients are different along the two perpendicular direction. And this pressure gradient actually gives rise to different acceleration along the directions, okay, along x and y axis. So this essentially gives rise to this kind of picture that we have momentum space anisotropy. And in actual hydro simulation, you can track the evolution of this spatial shape as a function of time, and as well as the momentum anisotropy as a function of time. And those quantities are called momentum space anisotropy and spatial anisotropy. And this is a real simulation result for gold-gold collision for impact parameter be 7.4 Fermi. The x-axis shows the time in Fermi, y-axis shows the momentum space anisotropy and spatial anisotropy. It's a measure of the deformation of space and momentum space. So as you can see, the spatial anisotropy decreases and momentum space anisotropy increases. That's what is expected from hydro picture. And that's another strong motivation for using the fluid dynamic picture, because over the year from 2000 up until now, we started with very simple hydro model of one-dimensional Bjorken flow, and then we gradually developed that further. We improved transverse flow, and nowadays we can describe transverse flow with initial lumpy condition, etc., and we can describe many flow harmonics as well. So all this success actually indicates that the hydro is probably the best, one of the best dynamical model to describe the heavy ion collision. Okay. Now, if you are wondering why we can apply hydro in such a small system, I would like to draw your attention to the fact that in laboratory experiment with few thousand cold atom, and it was observed a similar thing. Like you can initially trap the atoms, cold atoms, in a zone which is asymmetric, in shape, and then you can observe its time evolution as is shown here, and you can plot as a function of time the aspect ratio, that means the ratio between the semi-major and semi-minor axis, and this will also give something like the momentum space anisotropy evolution, or in this case like for this tabletop experiment. So it works, the hydro picture works for even smaller system. Okay, now
Victor,
yes,
if I can interrupt here a little bit.
yes,
So if you see, I had a question related to this small system. So
Mhm.
Landau's one of the assumptions is statistical equilibrium or thermal equilibrium. So if you see the cold atoms or in our PP collisions,
Mhm.
so the number of particles is very less. And
Mhm.
if you look at the lifetime of the hadronic phase or so that is also less.
Mhm.
So the meaning is there may not be sufficient time for thermalization.
Yeah, so that's okay. Yeah, you are correct. And these things should be investigated by using some first principle calculation, because hydro, it can only assume if there is equilibrium, then it will work. So in hydro picture, we
Correct.
cannot answer whether the equilibrium achieve or not. But yes, if we use the transport equation, then we can somehow give some idea what's going on, like by looking at the phase space trajectories and whether the phase space trajectory is achieving the hydro attractor solution or not. So those things are under investigation right now, and again this is for a long time, it's an open question, and people are trying to prove that yes, we can achieve the local equilibration.
And particularly when you take cold atom and try to describe hydrodynamically, so
Mhm.
this statistical equilibrium is always a question. So it describes that is fine, but a few number of particles or few number of cold atoms.
Yes. Okay. So from where the thermodynamic limit starts to apply, that's again, I think it's under mesoscopic physics or something like that. Because yeah, how many particles are few particles? Like
Right.
that's the thing.
And one more related question to your last slide, just it is a yeah. So last slide, if you go, so energy density you have used 30 GeV per Fermi cube, right?
Yeah, that was for gold collision, I think. Yes.
And gold collision, if I remember, it was something like 3 point something or below 5 GeV per Fermi cube experimental measurement. So in hydro, so you must be assuming initial energy density, and then when you confront to your experimental data, so you may be having multiple parameters like eta by S value and epsilon 0. Okay.
Yes. Yes.
So in that way, so what is the best value of initial energy density as estimated from hydro? I know it is an initial input.
Yeah. That also depends on the initial thermalization time that we use. Yeah, so I think that overall, like global fit will help us in deriving the base value. Okay, because we use a particular value here for initial time tau 0. So I'll be discussing about all these parameters for others. I'm telling this. I'll be discussing about all these parameters we use in hydro probably next day. So here, yes, you are right that these values are not very precise in the sense that there are other variables. Like if we change eta over S, then epsilon 0 will change. And this epsilon 0 is for ideal case, as per I remember. And the initial energy density will reduce for viscous cases because entropy is generated during the evolution. So we need less initial energy density in hydro model. Yes.
Yeah, although experimentally we take the formation time tau to be 1 Fermi always, because it cannot be measured experimentally. So with that assumption, even LSC measurement is around 14 GeV per Fermi cube.
Oh,
so
okay. So
0 looks a little higher. So that was my point.
Yeah, if you take initial time to be 1 Fermi, then this epsilon naught will come down quite a lot. Because here we have taken probably 0.5 Fermi or so, something like that.
No problem. Go ahead, please. Thank you. Thank you.
Okay.
Yeah.
Okay, now the question is why relativistic hydrodynamics? So far we have talked about non-relativistic hydrodynamics. Now we note a few points here. First of all, if the mass of the constituents of the gas or fluid is comparable to the system temperature, which is actually a reflection of average kinetic energy, then mass density is no longer a good degrees of freedom, since it doesn't take into account the kinetic energy part, which may be or greater than the rest mass of the particles. So essentially, you need to use the expression for energy for the full relativistic expression. So if you now, let's take this example. You want to calculate energy density for a gas of particles with relativistic speed. So if n is the number density and where epsilon here is the energy per particle, okay, so n epsilon will give you the energy density. Now energy per particle means here again a fluid particle, so that you can write as using the usual formula, and if you just expand it binomially, and then you see that you have the first term, which is the rest mass density, okay, and then you have other terms which are kinetic energy terms, and these kinetic energy terms we cannot neglect once we go to the relativistic regime. So essentially what we do for non-relativistic regime, our equation of state only contains relationship between the mass density and the pressure, but for relativistic case it should be different. And energy density, as you can see, you just have to multiply this above expression by n and you get the following expression. Now again, other point to note here that the fluid velocity itself may reach a few % of speed of light. And in those cases, we really need to use the concept of force velocity, because it then depends from which frame we are looking at, and we should use the covariant formulation of physical laws like tensor equations, which are Lorentz invariant. So that's why we need relativistic hydrodynamics. Now, what is the main difference? As I mentioned earlier, beginning of my talk, that I will be making analogy between non-relativistic and relativistic part. So in non-relativistic part, we have already derived this conservation of mass. And if you go to relativistic regime, it looks like following. Here, epsilon is the energy density, which replaces the mass density. And I will talk about B very soon. And the Euler equation, which is the equation of motion for non-relativistic case, now takes the following form. Here again, you see, U alpha is the fluid force velocity. Here it was 3 velocity. It is replaced by 4 velocity. And the mass density, now here it was the mass density which gives the inertia. Here it is the energy density plus pressure which gives you the inertia. And all these symbols, this capital D and grad alpha, are defined in this way. I'm not going into more details here. Okay, I'm actually running quite late. I have too many slides to cover. So I'll go a little bit fast. Okay. So what about relativistic viscous hydrodynamics? If you have viscosity, as we know that in nature, ideal fluid doesn't exist. Even superfluid helium has small but finite viscosity at the critical temperature, as you can see from this figure. So all fluids are viscous. So what happened if you extend the non-relativistic viscous theory to relativistic case? That was done by this guy Karl Eckert in 1940, and he come up with the formulation of relativistic generalization of Navier-Stokes theorem, but that was later turned out to be suffering from the problem of acausality. That means signal inside the fluid can propagate faster than light, and this problem was later resolved by these two guys, Israel and Stewart, during 1970s. Around 1980s, and they developed the well-known popular theory of second-order causal hydrodynamics, where you have the dissipative quantities are treated as dynamical variable along with the fluid variables. Again, I'm not going into details here. Okay, the other central part of relativistic hydrodynamics is the concept of energy momentum tensor. Okay, so what is that? Now, first we notice that fluid at rest has finite energy density and pressure. Let's take this fluid here. It has finite pressure. This is the energy density or mass density, whatever you say. Small epsilon is total energy by volume, and mass by volume gives you mass density. And this is related to the quantity, mass density or energy density. They are conserved things. So the mass density, as we have already seen, it is related by conservation of mass equation. and the pressure of the fluid is related with the Euler equation, that is which gives the acceleration of the fluid. Now, what happens to this energy or mass density when we go to relativistic system? So as we notice here that energy density you can define like energy per unit volume, and pressure you can define like force per unit area, which is again momentum per unit time, and area is intact here. So time times area is again a volume, but this volume is in space time. So it is essentially momentum by per unit volume, and this is energy per unit volume. Now all these quantities, energy, momentum, and these volumes, they changes if you go to a different reference frame. So under Lorentz transformation, they change. So that's what we need to take into account while we are discussing a relativistic system. And we know that physical laws must be invariant under Lorentz transformation. So we need to accordingly adapt our fluid equation so that it remains invariant under Lorentz transformation. And in that respect, tensors are of great help, because tensors are the quantity which shows this kind of behavior, that tensor transform under Lorentz transformation, but it remains, the physical laws remains invariant. Okay, so for our case in fluid, the corresponding tensor which in the rest frame will give us the energy density and pressure is the following. So that's what we call as energy momentum tensor. And energy momentum tensor diagonal terms gives you the energy density, the first one, and the other three terms gives you pressure. Okay, now if you apply a Lorentz transformation to that, essentially you are taking the rest frame T mu nu and applying Lorentz transformation, then you can obtain the T mu nu in any arbitrary frame. And I'm not writing it in matrix form, it will be cumbersome a little bit. So the form which takes, it's like the following. Here you see epsilon is the energy density, P is the pressure, U mu is the fluid force velocity in arbitrary frame. Okay, this is a tensor, this is in tensor form, and the corresponding conservation equation for this energy momentum tensor is written like this, del mu T mu nu 0. And that's what we work with in relativistic case. It is the analogous of the Euler equation and mass conservation equation, but because you can show that you can derive those equations from the energy momentum conservation. How much time do I have? It's 52. Okay. Okay, now one thing I have missed so far, that is the equation of state. I only mentioned briefly initially. Now let us see why we need equation of state and how it is connected to the microscopic world. So probably, I mean, in the previous slide, as I mentioned, T mu nu, which is the energy momentum tensor, it actually gives you the fluid variables, like as is shown here. So this T mu nu, when you write in general form, it will have all non-zero elements. And as you know, the 0,0th element will give us the energy density, the diagonal element will give us the pressure, and these terms will give us the momentum density, and these other terms in the column, they will give us the momentum flow or momentum flux, and they are part of what is known as shear stress, shear and bulk stress. And the column here under the energy density, they will give us energy flux. Okay, so this is the interpretation of energy momentum tensor. Now we need an equation of state. Why that is so? Let us see for ideal case only. So we have this conservation equation for fluid. Here we have 4 equations because mu is anyway summed over index. So mu is the free index, and we have 4 free indices. So we have 4 equations. And in the definition of T mu nu, we have 5 unknowns. Those 5 unknowns are energy density, pressure, and U mu actually has 4 components, but the normalization condition that U mu is equal to 1, that gives a constraint. So you have 3 variables here. So 3 plus 2, we have 5 unknowns. So the system of equation is not closed, and that is closed by what is known as equation of state. That means the relationship between energy and pressure in this case. Okay, now let us look at the equation of state from the microscopic perspective. As I mentioned, this is the only place where the fluid takes into account the microscopic nature of the system. So maybe water is different from benzene, and benzene is different from Quark-Gluon plasma, but they all are fluid, but they are different in this aspect that their equation of states are different, and also the other transport coefficient may be different. So let me go through very quickly, and I will stop here after discussing this slide because I'm running out of time. So now T mu nu, we can also construct from the second moment of distribution function. Now, what is distribution function? It's a it corresponds to the fluid part. So in fluid picture, we disregard the momentum distribution of the particles of the fluid. We only care about the space-time variation of thermodynamic variables. But in kinetic theory, which is the microscopic theory for the fluid, it takes into account the momentum and spatial variation of the phase-space distribution function. So that F contains the microscopic information, and T mu nu is the second moment of this distribution function. Now you can write, because this is a second rank tensor, P mu P nu gives you a second rank tensor, the outer product. You can write in terms of your basic variable of fluid, which is U mu, and delta mu nu, which contains essentially G mu nu, the metric, and U mu nu again. Okay, so this is how we can decompose T mu nu. And here A0 and A1, they are unknown constant. And if you make a comparison with the T mu nu here, the fluid, we know, then you can recognize that A0 is nothing but epsilon and A1 is nothing but minus P. We can see that in a different way. So by definition, A0, you can figure out from this expression, if you multiply both sides by U nu, then you get the expression for A0. And that is given by this following expression. And A1 is similarly given by taking the product of delta mu nu on both sides. Because the delta mu nu is perpendicular to U mu, this term will be 0. And only the non-zero term will be the coefficient of A1. Okay. And that is what we are getting here. Now, this expression, you need to use the actual form of distribution function. Now we are using here a massless Boltzmann gas. That's the simplest possible case. You can also use Bose-Einstein or Fermi-Dirac case. Now in this case, we know the distribution function takes the following form. And if you plug in it into the expression for A0, you can do this integration, and it turned out to be the following expression: 3 by pi square times temperature to the power 4. What about A1? A1 turned out to be minus 1/3 of A0. To do the calculation in details. And if you note that A0 is energy density and P is pressure, then this relation between A1 and A0 actually is the relation between pressure and energy density. And for this case, it's 1/3 of epsilon pressure. And that is the well-known equation of state for a massless Boltzmann gas. Okay, I think I will stop here today, and I will try to finish the remaining part in, tomorrow. If you have questions, you can ask me.
Hello, sir. Can I ask a question?
Yes.
Yeah. So, okay. So you talked about this kinematic viscosity, where in a non-relativistic case we take actually eta by rho, where rho is mass density. So in a relativistic case, we actually take eta by s, where s is entropy density. So wouldn't it be better if we took like energy density in relativistic case instead of entropy density? So why is that we are taking entropy density?
Okay. First of all, it was used to make this thing called dimensionless thing. Dimensionless parameter eta over s was used in terms of h bar 4 pi kb, etc. And I think it's the reason is the same. Like eta over rho, we make it in such a way that we get the dimensionless things. So essentially, if you go to the, okay, maybe I should put in this way. Eta over epsilon, epsilon won't give you the total inertia of the system. As you can see from the equation of motion for relativistic case here, you see epsilon plus p, it always appears as a inertia, okay, for relativistic fluid. So whatever rho was playing a role for non-relativistic fluid, it's the epsilon plus p, okay. So this thing you should consider, not only energy density, that's the first part. And the second part that you consider only S, that is, I think that's coming due to the fact that it will make this thing a dimensionless thing, if you consider S.
Okay, yeah, understood. Thank you.
Okay, thanks a lot, Victor. Maybe we can take up the rest questions if there are any through offline, through emails, or in tomorrow's lecture. Is it fine?
Sure, sure. Sure.
Okay.
Okay, thank you all. Thank you all.
So then we move to Victor. Thanks a lot. And
Okay.
we